In Module 1, we explored how to design logic systems that produce outputs based solely on current inputs. Now, in Module 2, we'll explore systems that retain information, make decisions over time, and interface with real-world devices. Here's what we'll cover. Routing and selection devices in more detail. Introduction to microcontrollers. Basics of assembly language programming. Input, output, I/O, control of microcontrollers. Sequential logic, latches and flip-flops. Registers, microoperations, and counters. Memory types and organization. By the end of this module, you should have a conceptual and practical understanding of how hardware and software interact in a computer system. Section 1, Routing and Selection Devices. In Module 1, we touched on decoders, encoders, and multiplexers. Let's go deeper. Decoders. A decoder translates an n-bit binary input into one of two possible outputs. Think of it like a traffic director, only one output line is active at a time, depending on the binary code at the input. Encoders. An encoder works in reverse, given multiple active inputs, it produces a binary code corresponding to the active line. Priority encoders resolve conflicts by assigning priority to the highest order active input. Multiplexers, MUX. A multiplexer selects one input from several sources and sends it to the output. It uses selection lines to decide which input to pass. Demultiplexers, DeMUX. The opposite of a multiplexer, routes a single input signal to one of many output lines. Section 2, Introduction to microcontrollers. A microcontroller is a small computer on a single integrated circuit, containing a processor, CPU, memory, input, output, I/O, ports. Microcontrollers are designed to perform specific control tasks in embedded systems, for example, in washing machines, printers, or thermostats. Microcontroller versus microprocessor. A microcontroller has CPU, RAM, ROM, and I/O on the same chip. A microprocessor usually needs external chips for memory and I/O. Relationship to assembly language. Microcontrollers execute machine code, but writing directly in binary is impractical. Instead, we use assembly language, a human-readable low-level language that directly corresponds to machine instructions. Section 3, Introduction to Assembly Language Programming. What is assembly? Assembly language is the bridge between human thinking and hardware execution. It uses mnemonics like MOV, ADD, SUB to represent operations. Basic assembly concepts. Registers, small, high-speed storage locations inside the CPU. Opcodes, the operation code telling the CPU what to do. Operands, the data or addresses the operation acts upon. Labels, used for marking locations in code. Example. A very basic assembly snippet might load a value into a register. Perform arithmetic. Store the result in memory. Section 4, I/O control of microcontrollers. Memory mapped I/O. The CPU treats device registers like memory addresses. Writing to an address sends data to the device. Port mapped I/O. Uses special CPU instructions to read/write I/O ports. Digital versus analog I/O. Digital I/O, on or off, high or low voltage. Analog I/O, continuous range, read via analog to digital converters, ADC, or generated via digital to analog converters, DAC. Section 5, Introduction to Sequential Logic. Unlike combinational logic, sequential logic has memory. The outputs depend on both current inputs and past states. Latches. The simplest memory devices. SR latch, set/reset. D latch, data latch, captures data on enable signal. Flip-flops. Edge-triggered devices. D flip-flop, captures data on clock edge. JK flip-flop, more flexible, can toggle state. T flip-flop, toggles every clock pulse. Section 6, Registers and Microoperations. Registers. Groups of flip-flops used to store multi-bit values. Registers can store data temporarily. Shift data left or right. Hold instruction codes. Microoperations. Small steps that make up the execution of a single instruction. Register transfer, moving data between registers. Arithmetic operations, performed by the ALU. Logic operations, and, or, not, XOR on register contents. Section 7, Counters. A counter is a sequential circuit that advances through a sequence of states. Types include binary counters, count in binary. Decade counters, count 0 to 9. Up/down counters, count in both directions. Section 8, Introduction to memory. Main types. ROM, read-only memory, non-volatile. RAM, random access memory, volatile. Cache, small, fast memory between CPU and RAM. Flash memory, non-volatile, rewritable storage. Memory organization. Word size, number of bits processed at a time. Addressing, each memory cell has a unique address. Access time, how fast data can be retrieved. Volatile versus non-volatile. Volatile memory loses data when power is off. Non-volatile memory retains data. In this module, we've explored routing devices and their functions, microcontrollers and their relationship to assembly, basics of assembly programming, I/O control mechanisms, sequential logic and memory devices, registers, microoperations, counters, and memory systems.